Bernoulli's. This is usually where I start out examples in my base class because the likelihood of Bernoulli and the sampling distribution look extraordinarily different. Where normal distributions, the likelihood and the distribution look extraordinarily the same, they're just shifted in different places, so that can be confusing to people. So we'll be going through that a little bit later, but I do like Bernoulli's. Might as well just do this. Make sure that we know how to do this. I guess there's lots of ways you can do it. Let's just first think about maybe what's the variance of the individual xi's. This is probably how I would do it because it's an IID problem. And so how do we figure this out? I guess we just work through the expectation of the xi squared minus the expectation of the xi's all squared. And we can just take these to the definitions. So use the definition on all these things. So the expectation of x, how do we figure it out?
Your sum. If you want to.
It's 1 times.
Yeah, you could just do the sum, right? So this is pretty easy. So I'm just going to look over all of the different xi's with the associated probabilities of these things, right? So that's it. So the i's could be 1 and 0. So 1 or 0. And so this is equal to sum of the 1 times p plus 0 times 1 minus p. Done. So just back to the original thing. If I wanted to figure out the xi squared, that's not too hard. So expectation of x squared is just equal to 1 squared plus, times p plus 0 squared times 1 minus p. So you can work through that, put this all together, do some squaring, add these things together, and you'll come up with p times 1 minus p. So if you just take those two bits, do some algebra, plug these things together, that's p, but you're going to square out one of these so you see the square. So if you just roll that p through. Anybody confused? Chris? Good to go, right? That's the blank stare, really. I can do.
I was wondering if we had to do this much detail in the test.
Sure, if I asked you to drive something and it's 2 seconds, why not? How would you explain it to somebody? But if you just wrote this down, this is not going to make any difference. So I'm okay with that, but can you drive it? I don't know. When you drive it, you just write it down, or how do you get there? So I think showing the little steps in the side lets me know you know how to take this back to first principles and just work these things out. So anytime we kind of work through an expectation or a variance or anything like that, you should probably make sure you know how to do it. So this is the sort of stuff. So, you know, if you made a mistake here, I would kind of be surprised because I would think we know it, but I can understand if you haven't had a class for a while. You might have forgotten. But if I can see these steps, then I know where you're going wrong. So that helps us all out. So it's just a matter of communication. So I tend to think tests are about communicating back and forth. I remember this one time when I was in college. I know I sound old. So when I was in college, I had taken this exam, and I was just like you guys. I messed up a problem, and oh man, I walk outside, I'm bummed.
And you already know the answer.
I know the answer instantaneously, and in fact, I had already done all of the math on a different problem, and I made a small mistake, because you know how these problems kind of roll into each other, and there's patterns. And I made a small mistake, and I said, yeah, but I did all the math on this problem. But then I didn't do any of the math here. I just wrote down the answer, and I wrote it down wrong. But I was recycling the answer. And the TA told me something really valuable. I'm sorry, I'm not going to give you the points back. You already got an A on the exam. But exams are about communication. Being able to communicate where your errors are and what you're thinking about is the name of the game. So I think so. I mean, this isn't too much detail, is it? Okay, so I think so. And then of course we gotta just do change this not just to the xi's, but the sum of the xi's. So I could have started with this, I guess. Sum of the xi's over n, and work this out, but I like to work it out through the elements because I know things about IID, random variables. So this is equal to sum, one of the, over n, variance of the xi's, and I can drag out the n, and when I drag out the n, I square it out. So I know what these are, everything's IID, so that's p times 1 minus p, that's what we would have derived if we felt like doing the algebra. Hopefully you can kind of see it all work out. And then I end up with sum over n of those things, so it's n times that divided by n squared, and we wind up with p times 1 minus p over n at the end of the day. So if you'd like, n times p, 1 minus p divided by n squared. I don't know if I need that detail, I can see it. So if you just go from there to there. Anyway, easy stuff. So let's just warm it up and get into doing some periodic quizzes. I'm going to check just to see that you're here, paying attention. If you're absent periodically, if you skip one of these or something like that, it won't hurt you. So I'll just say right now, if you're out for one of these, I'll just delete your lowest score on this. This isn't meant to hurt you a lot. It's meant to just check to see that we're on pace. So all of your homework, all of your quizzes, things like that, so long as you do it, and if you make mistakes, you're willing to redo it, it won't affect your grade. So if you're all not turning in the homeworks and you're doing poorly on things, that would affect your grade. So I'm going to just skim through these. I'm not going to return them to you. You know how you did. And really, realistically on this quiz, I'm just going to put a check in there and make sure you've done it, and I'll make a note to myself. So I'll say for our first one, this will have 0 impact on your grade, just as long as you've taken it. Fair enough? Okay, we'll do something more complicated next week, maybe based off of the homework. We're going to use this result. I want to go through the delta method. I want to go through a proof. I want to go through some examples where the delta method works particularly okay. We're going to need to establish what that means. I could probably show you examples where it works particularly well, but I never like to do that. I like to show you cases where it kind of works in some settings so you can kind of see the pros and cons. You don't really understand this that well until you compare it to something. So understanding if a technique is good is a comparative thing. So I will be having you do a simulation study on this. Let me just ask you, do you want to see an example first, or do you want to see a proof first? Who are you? Examples? Anybody want to prove first? How are you pretenders? Okay, I could go either way. I can see the value to both of them. Really, you're going to iterate these two things, like when you read it in the book. There is no correct way. Let's do example first, just because that's the majority. We'll pretend to be democratic today. Sometimes I like proof first. I used to like it more in the beginning of my career because I followed a pattern of, I don't know what I was trained in college. So let's do example first. Let's first state the delta method. Next time we'll look at an example that just fails miserably, and we'll motivate the second order method so we can just see some distinguishing qualities with the first order method and the second order method. I think we already answered that question, why we don't combine the two orders in one thing. And it's because everything doesn't work out to be normal. We'll see that better on Wednesday. So the delta method, let's just say what it is. So the delta method says, so here's the statement. If we have a sequence of random variables, yn, and here's an example. So x bar n would be an example of yn that has this property. It's asymptotically normally distributed. So a sequence of random variables is a stochastic process. A good example of a stochastic process is just a sequence of coin flips. So when you hear stochastic process, it means it's just repeating some random thing. So I remember when I took my first stochastic process class and I was like, ooh, we're getting into fancy stuff now. Now I can say words that I didn't even know how to say before. So that other people don't understand. Now I use it in common language and I say, oh, it's a very stochastic. And my friends are like, what are you talking about? It's like, learn some words. I mean, it's random. So it's variable. So just a sequence of just simple things, that's a stochastic process. Probably say a lot about this mathematically, but inherently it's really a simple process. Right here, if I'm thinking about Bernoulli coin flips. I just want this to have this property, square root of n, yn minus theta, where theta right here is the expectation of yn. So I'm thinking about maybe things that are IID and they have the same means. So I might say that this is an IID process. And this thing is going to converge as n goes to infinity to a normal 0 sigma squared. Oftentimes I'll put the sigma downstairs, roll that thing to the downstairs, and call this a normal 0, 1. Same thing. This is just the variance. Keep in mind this is the variance of the individual y's. So i.e. in our example, these would be the xi's right here that we're putting in here. So the divide by n shows up when you take the average. So that's the individual elements of maybe this IID process. So in our Bernoulli example, that would be p times 1 minus p. Where the n go, the n's over here, right here. Okay. I used to hate the whole standard error, standard deviation thing, because I would just think it's standard deviation of just a different random variable. Why don't we just be specific and just have one word? I don't know, people like as many words as they can to overload notations. So the delta method says this. If we want to consider a transform, we're not putting restrictions on what this transform is. However, so this is just a function g where I'm going to insert something into it. So I'm just leaving that open. What am I going to plug into it? The yn. I'm not putting any restrictions on this transform, but certainly the transform itself will determine how well the method works. So it doesn't work just as well for all transforms. That's probably true even for our Bernoulli example. How well does x bar work in estimating p? Probably has a lot to do with where true p is. So it's not like a normal distribution where wherever true mu is, it doesn't really matter where true mu is. We're going to have uniform performance if we use x bar to estimate mu, but for a Bernoulli, that's not true. Depending on how close you are to the endpoints will determine how well it works. And you'll get to simulate this and see the performance. Stuff that you don't see in the asymptotics, it affects the constants, but the constants are a big deal. So consider a transform G. Then we're going to have, here's our then statement. We'll say this is if this is true. Then GYN minus G theta, that's the mean, divided by, I'll write it the same way, times square root of n. But that embraces, this converges to a normal distribution, mean 0, because I've already subtracted that off. It's going to have a variance, and there's one other part right here, G prime theta, and that gets squared. So that converges to that, is n gets big. Let's just be clear about this limit. So if that's asymptotically normal, then this is asymptotically normal. This is pretty strong statement. As n gets big, how big does it need to be before it actually kicks in? For a Bernoulli example, it really depends on how close you are to the boundaries, how fast this normality kicks in. So the delta method can fail for all kinds of different reasons. We're going to be considering a linear approximator of our function to prove that this is true. So we're going to do some Taylor stuff. We haven't said anything about Taylor's right here. Obviously, we're saying something about the first derivative existing, and there's probably some caveats on that not being 0. So that's going to motivate the second order method. If that is 0, there's something else you could do. And we'll talk about that, but I won't test you on it. But I still want you to read through because I think it helps you to understand the first order method, where it works well and where it fails. So there is some statement about derivatives existing. What's hidden in this is when you derive this, is there's some statements about that remainder term in the Taylor expansion. And that'll determine how well this thing works because it determines the error. So all these things we really need to check. If I ask my old mathematical asymptotic friends, how well does this work? And they would say, works great, so long as n is really big. How big is big? Theoretician wouldn't have any business knowing anything like that. It depends. So you kind of need to check these things. Okay, let's see if we can work through a proof. So we're going to approximate using our first order Taylor. We'll approximate G. With a first order expansion. I feel inclined to take just a quick break because the book goes through all of this. They don't do anything with it at the end of the day. The higher order form, the way I've written this out is just everything's scalar. In the lecture last time I was going through some of the preliminaries where everything was vector. So I think before we jump into this, I want to just talk about the multivariate version of this, although the book doesn't take this very far. They just want you to know there is a multivariate version. So let's just spend a moment chiseling away at some of the properties of the multivariate version, and then we'll jump back to this scalar version. So this is the scalar version. It looks like this. G of yn might be G of theta, so that's our centering parameter, plus G prime theta. This is going to be yn minus theta plus a remainder, and I'm going to call that remainder Rn. And you know what the remainder terms look like. They're the higher order terms. We'll come back and address this. We need to spend some time talking about that remainder. The multivariate form looks like this. This is from last time. We were just discussing some random variable t, looks like that, tk with means. I'll say the expectation of each ti is equal to theta I. And then we can put this into vector notation. Theta 1. Up to theta k. I guess I was calling this cap k last time. I'll try to be consistent. So there is a first order expansion. I like that you get to see it. So that's the only reason I'm presenting it. I don't want you to be overly confused about what the book is saying. So there is a multidimensional analog. They don't fully derive it. They derive everything in the scalar form just to reduce some of the overhead. I think that's okay. So that's where we'll stick this thing. But again, I think it's useful just to see the first order Taylor expansion. So first order expansion. So G of T is going to be approximately G evaluated at cap theta. Cap theta is multivariate, but when I evaluate it, it's scalar. So I'm evaluating it and I'm just turning it into a number. So this looks like this. G prime I evaluated at theta, Ti minus theta I. So that's just the first order thing. I goes from 1 to cap theta. So somebody said, why don't you do the thing that they told us back in calculus class, where you figure out what the gradient vector is off of the tangent, and then you come up with a tangent plane estimation of all of this by dotting the gradient vector into the positional vector. That's exactly what this is. So if you understood everything that happened in calculus class, that is the approximation. It's the planar approximation to whatever G is. Works really good if that function is flat. It looks like a plane. Plus some remainder. And we know what the remainder looks like. I'm not going to write it all out here just because the second derivatives we'd have to do all the mixed partials. See?
How would you notationally write out the gradient form? Because I know it would be basically just the nabla symbol with the G.
So what you end up doing is you dot this thing into, you have this intercept, you dot this thing into your positional vector, append with 1 instead equal to 0, and that means you're picking the perpendicular to everything.
Right.
So, same thing they taught you in Calc 1. So you could write that out, bless you. That is a dot product. All sums are dot products. So I'm gonna leave it in this form. So, but it's the same exact thing. If you want to talk about that in a review session, I guess we could do a calc lesson. I think I still remember how it worked out. So, cool. Let's just look at how good this approximation is. This is what we did last time. Somebody's already having a bad day. This was from last time. Expectation of GT is going to be approximately expectation of G theta plus our derivatives. Ti minus theta I. How good is that approximation? We don't really have a good understanding of it. We just wrote a symbol down. So it kind of means nothing at this point, but maybe they're close. So that's just expectation. This is just G theta. So all we've done is taken the expectation, slid it across here. The only thing that's random is the T. So expectation slides over everything else. We don't even have to do any expansions because everything's in linear form. And just recall that the expectation of Ti minus theta I is equal to the expectation of Ti minus theta I. Expectation of theta I is theta I, because it's just a constant. This thing is theta I. So the expectation as it rolled over that gave you 0. This thing is 0. All of those summation terms are 0. Where we left off last time is we wanted to look at the variance. Let's just glance at that. I like this because it just teaches you some basic properties. Where the heck did this thing come from? Again, it's always just first principles. I usually just do what I learned in Stat 101 or some class like that. Same exact techniques, useful then, useful now. Sometimes they're useful now. So the variance of GT is going to be approximately the variance of G. Let me write it out this way so you can see where all the terms come from. This is going to be equal to expectation of GT minus its mean right here. Now there was an approximation right here. So this isn't equal. What would be equal right here is if we wrote in the expectation of GT. So there's a series of approximations that the book just runs through real quickly. And they expect you to understand that. That's the definition of variance. So if you're like, where did that come from? Def. So expectation of the function, the square deviation of the function from its expectation. The expectation of that is variance. So that's the definition of variance. So this thing is approximately expectation GT minus, I'll deal with this one here. So we've already said something about that, G theta. Squared. So already an approximation. Now I'm going to add my later approximator right here. So this is going to be approximate again. Expectation of G theta plus sum I goes from 1 to cap k, G prime I, these are I partials, Ti minus beta I, minus G beta. Some cancellation. This is equal to expectation sum, this is squared, I goes from 1 to cap k, Gi prime theta, Ti minus theta I, squared. I think this is what the book does. They say, boom, boom. So, am I expecting you to fill in details on things? My guess is you like when books fill in details. Anybody stuck on any of the details right there? I see stuck faces. Where's the, hang on. Everybody good? Chris? You're deep in thought.
That forward should be outside the front.
Oh, that one is there. Okay, that would be confusing. Yeah, it didn't magically slide in. Was that it?
Yeah.
Okay, cool. Yeah, anytime, like I'll scan your faces for a minute, and if I see particularly being puzzled, I'll stop it. It probably is a mistake. So, little approximation there. We included that thing, the intercept subtracts off, and you come up with this thing. How good, what is this thing at the end of the day? We can write it out. Probably another opportunity for a quick Stat 101 lesson. But this thing right here is equal to, again, I've approximated twice, so this is really an approximation. I don't get to recover that equality sign later on. Just like proportionality signs, as soon as I write it in once, that's all I got at the end of the day. So this is going to be G, this is going to be sum. I goes from 1 to cap k, G I prime theta. This gets squared. This is the variance of the TIs plus 2 times Gi prime theta, Gj theta prime times the covariance of Ti, Tj. You're going to sum over all of those pairs. So I'm going to put a little summation sign in here. I'll take the 2 outside and sum. Let's see if I can make this a little messier. 2 times double sum. And the way I like to, oh my goodness, I less than j. I'm going to rewrite all of that just because it looks so messy on the board. Variance of GT is approximately sum, I goes from 1 to cap k, GI prime, evaluated at theta, squared, times the variance of the TIs, plus 2 times sum I less than j. So I'm going over all the pairs and I'm making the i's less than j and multiplying by 2. If you don't like multiplying by 2, you can sum over all ij pairs. It's just that it's symmetric, so a bunch of these things I'm just getting added up twice. So gi prime theta, gj prime theta times the covariance of Ti, Tj. And if you want to be really pedantic, you should make those capital. So, to talk about the random variable, because that's how you first expressed everything. You'll see people flip back and forth. So, just depending on if they're talking about the space or transforming the elements, but they transform exactly the same. That's why people get confused. It's like, it's not the same concept, but it's immediately extendable. It's about as similar as you can get without being exactly similar. So if you feel like making those cap t's, because I did that over here, you can do that. So Ti, Tj. Yeah. If you don't like that, let's just do this for k is equal to 2. Let's do another quick Scout 101 lesson. If I asked you to show that this is true, I would ask you probably for a grad school induction proof. What I mean by grad school induction is you show it for the minimal thing and you just kind of know in your head it all extends. I'm good with that. So in this class, if you can show it for one thing and you can kind of see the algebra always works out the same, that's good enough for me. So Colby's upset because he's like, my math teacher was much harder than that, and I expect you to be too. Sorry to disappoint. So, but you get what I mean. Like, you get it. So let's move on and apply the concept and be statisticians and not necessarily perfect mathematicians. So this is just going to be the expectation of G1 prime theta, T1 minus theta 1 plus G2 prime theta, T2 minus theta 2. This is all squared. So this would just be the special case. So pretty easy stuff. We're just going to FOIL everything. I've never said FOIL since high school and then when I started teaching grad school. Now I just say it, I think you all know what I mean, but you expand that thing right here. So that's just the expectation of G1 prime theta squared, T1 minus theta 1 squared, plus G2 prime theta squared, T2 minus theta 2 squared, plus 2 times our mixture. This is 1. G prime 2 theta, T1 minus theta 1, T2 minus theta 2. And now you can kind of see it. So when I slide the expectation over this term, I'm going to wind up with G1 squared, G prime theta squared. I think the reason I have such a hard time with that square is I already do something in the exponent. So then I give up on it. So this is going to be the expectation. Once I slide that expectation over, T1 minus theta 1 squared. That's the definition of variance. T1. And if you want to make them cap t's, go ahead. So that's just that variance. So that's this first term that we see in everything. We get the sum of all of those. You'll get another one here. And then when I slide everything through the expectations, I'm going to wind up with these things factorizing out. That's all of this stuff. There's my 2 because I didn't add up the term twice. I just knew they were the same terms. I added them twice. And the expectation of this mixed term, T2 minus beta 2. I'll put braces on there. That's just the definition of covariance. I know what you're thinking. Geez, I hope you don't do a high dimensional example on a test because figuring out these covariances can be hard. The book barely even does this. They've got a problem in the book. So I think I just want to show you all this delta method stuff can extend. And obviously the variances are a matter. It's important. We can even wrap this up with a normality claim just by looking at a similar analog to what I'm about to prove. So that's just the high dimensional version. Let's just leave it there. I think if you were the 1960s, I would say keep this in your back pocket because you're going to use it on some examples. I think what we're going to figure out in this class is this is an okay technique some of the time, but I wouldn't rely on it. Sam?
I was just wondering about the little I is greater than J thing there. And I was trying to figure out like why is that there?
I didn't want the 1-2 term and the 2-1 term.
That's what I was thinking. It was the fact that you have that.
Yeah, it's just that symmetry. So I could have summed over this term and had the G1, G2 term and then the G2, G1 term. But instead I just wanted the G1, G2 and multiply by 2 because they're the same.
So if you took out the 2 and then you summed over all the i's,
Yeah, this would be equivalent.
Okay.
And you'd be counting stuff up twice. If you did it on your code, you just have double time, which is asymptotically irrelevant, right? Tell that to your grad advisor. So you waste a lot of time doing these sort of things, but yeah, they're exactly the same. What's that? I not equal to J. Yeah, you're right. I could get rid of that term right there and keep the I equal to J in there because that's the same thing. Okay, so we've got the high dimensional version. Let's butter up the proof in just the scalar version, and I'll imagine that you know how to do the higher dimensional version. I'm not going to test you on it, so it's not a trick. So it's just coverage because the book is covering it. We're going to get closer and closer to the book as we go through chapter 6 and chapter 7. Let's do an example before we do the proof of the delta method. So let's just remember what the delta method said. It said if the random variable was asymptotically normal, then if I transform the mean in the random variable, it's asymptotically normal, but I have to rescale everything by that derivative term, and it gets squared. Let's just write it down. So root n, yn, minus theta goes to a normal 0 sigma squared, and root n g yn minus g theta goes to a normal mean 0 g prime theta squared sigma squared. So I'll just do some example like this. I could use this like this. So this is wrong, but this is how you apply this. So how you might apply. Is we might say gyn, and this is an approximation. Approximately normal. No asymptotics there, you'll see in a second. This is going to be g prime theta. I keep calling this, I keep mixing this up. It's really just the scalar theta. There's my square that I almost always forget, times sigma squared where this is the variance of the elements. Of maybe the yi terms that evolve in the sequence. So this is approximately true. It's not exactly true, obviously. Oh, this is divided by n in here. If you want to put the n over here, that's probably where you might want to stick it. So I can't take a limit to both of those sides, but this is how you might use this thing in practice. So how is this test statistic distributed? Close. It's kind of like saying x bar is like a normal and using it that way. So later in chapter 10, which we won't get to, we're just going to vary it in right now. They show you what a pivot is. And they show you how to apply this stuff in practice. We're going to kind of start with that, and I'll show you right away what it is. Later in chapter 8, I'll define it for you. So let's just look at this example. Bernoulli P, I goes from 1 to n of those. So what I'm going to do is I'm going to come up with my estimator. P hat is equal to x bar n, and say we're interested in this. We're interested G, this function right here, I'll say this is just P over 1 minus P. So that's just the odds. If I plugged in P hat into that, we'd still have a definition. I haven't said any which way what you have to plug in there. I can plug in happy faces, and those would just be happy faces where the P is. So same exact thing. What we need to do to apply this, so I might say x bar n over 1 minus x bar n. This is approximately normally distributed. This is going to have x bar, whoops, this is going to be p over 1 minus p. So I'm just doing a substitution. Where I see x bars, I just replace with p's. Now I need the derivative, dp, p times 1 minus p, of p divided by 1 minus p. I need to square that derivative out, and then I need to plug in this variance. So this might be my variance for my x bar n. And we've seen that before. Divided by n, that's where we started class. So I'm just going to plug those things in. It's just a probability statement.
Do you need these to be IID?
Yeah, so back to that rule, if I don't say it is.
Okay.
So if I don't show you the mechanism of dependence, what else could I have meant? I get it, everybody else in the world feels the need to tell you that every time, even though, what does it depend on? Yeah, they're IID. We don't technically need everything to be IID, we just need that statement to be true. But we're using an IID example. So that's what we do with it. This is kind of cool. Okay, that test statistic is distributed like that. I'll show you how people use this as an inferential tool next time when we kick off. And basically what they say is something like this. If I'm trying to understand this quantity, then maybe I want to understand where it's centered. It might be centered here. And then I need to estimate all variance terms, but I would need to know P to understand what the variance terms are. So I can't actually do anything with it until I can know what P is. So what people do is they replace all the P's with x bar in there. That's what's called pivoting. There is a formal definition. There are properties of statistics you can use for pivoting, but basically you're just replacing. So we're going to come back next time and flip this around and show what we might do with the sim study. But this is just a probability statement right here. How do we use this inferentially? Well, we basically just flip the roles of everything. And that flipping the roles of everything is what people do to create confidence intervals. So there's lots to talk about there. If that seems weird and spooky to you, weird and spooky to me too. So I know what it means. It just means that the interval itself is random. We're not saying anything about the actual true value of anything. We're talking about coverage. So we need to wait until we get into chapter 8, but all that stuff your Stat 101 teacher was telling you about. So what I want to do next time is talk a little bit about this, a little bit more, what you're going to be doing with this on your sim study. This is exactly what you're doing. We'll probably work out that derivative, so we have a closed form. I just didn't want to do the product rule or the quotient rule in the last minute, and then we'll prove everything. So if you want to run through the proof in the book, it's actually a lot easier than the central limit theorem proof. It's really only about 2 or 3 lines, but you have to say something about the remainder doesn't matter. So that's the part you're going to be focusing on is, why do we get to get rid of the remainder on everything? So, and you're going to have to be looking at the scaled linear term to really figure it out. That's the discussion we'll have next time. So thanks so much for indulging me. So I'll give you many more opportunities to practice your skills before we get to a real midterm. That's it for now, you guys.